Okay, so in this entry of xaq-ai Diaries, I introduced the Picrawler, and that is the most exciting part for me because I've always been interested in robots with legs and I've always wanted to make them work. So you're going to start to see me build out the Picrawler and start running those tests. And you're also going to see how I fall into the reinforcement learning trap and the number of sliders on the screen grow and grow and grow. Let's check it out. Okay, check this out, kids. I really hope, not like version 3 kind of hope, but for real hope and believe that this thing is actually learning based on all the crazy principles that I've been applying to this thing. Okay, so what you're seeing right now is my little quadruped learning how to stand, and it does learn how to stand. You're seeing a couple things on the screen here. I've got a good boy and a bad boy button. I haven't even used this yet. Everything right now is still learning on its own. No tricks from the outside, but Claude and I agree that there's a couple of levers that we should be able to pull in order to control an autonomous agent. There's no arrow keys say go left, go right. Everything is going to be goal, reward oriented, right? So what I've set up right now is basically a curriculum player that has to meet certain milestones, and then this reward policy changes depending on what the thing is that I'm trying to accomplish, right? So right now, we want to keep the reward at a certain, I want to keep the body at a certain height, right? It's learning how to stand. Right now, the chassis is like 0.05 meters above the ground. My target is 0.085, right? And also it'll get penalized if it tries to go too high because there's a chance it could fall over. Now, what I've seen is that this thing will continuously learn how to stand for many minutes at a time. Super excellent. I think what I need to do right now is actually change these metrics to show me the actual numbers. I see yes, we have a reward shape, but what is the actual value? Right, so I know what the value is because we set it in the background. But anyways, I know that the chassis height should be within a few degrees, or the chassis height should be within 0.85 meters. The degrees should be within 20 degrees, and right now I have auto reset on if it flips itself over, so it can go back to the center and continue learning, right? So I can let this thing run for hours and hours and hours, and it actually gets better. That's what's crazy. I've done multiple ablation tests to see what it is that it's actually learning, right? So the pre-motor controller, here, let's just flip over to the graph and look at it. So right now, the way it's wired up is that here are the actual motors. Ooh, it looks like it flipped over. I saw that happen in the background. Yep, so it started over. It had a flip. Not a problem. But basically, there's 12 degrees of freedom, right? So this is actually based off of the Picrawler. Here, let me go grab it. I'll show you. My reward for getting this working is actually building this guy, right? So there's 12 degrees of freedom. There's a hip joint that pivots on the yaw axis. This took forever to build inside of Godot. It was very confusing for Claude to figure this out. I could have probably done it faster by putting the model together myself and rigging it in Blender, even though I don't even use Blender. That's how long it took, but eventually we figured it out. So yaw, there's a hip 2. So this would be hip 1. Hip 2 is this vertical pivot that's very close to hip number 1. So hip 1, hip 2, and then there's a knee joint, right? So there's 3 servos per leg. That gives me 12 degrees of freedom. And that's what we're looking at right here, right? So we've got all of the servos wired up here. We're doing kind of a sim to real thing. We have it roughly the same weight that guy will be with a battery in it. All of the servos are roughly the power and dynamics of a real servo. We're trying to model that so that we can actually go to that guy eventually. But what we're actually looking at right now is, so we've got a pre-motor controller for each leg, I believe. Let's see how we have this. Pitch, 1, 2, 3, 4, 5, 6. Yeah, so this is wired up basically. Let's see what we got going on here with the pre-motors. Looks like it's pairwise. Yes. Right. Okay. So we've got basically a pairwise motor controller thing. This is something that we need to experiment with, right? So each hip has its own motor controller, but then each leg joint has the two knees, the two horizontal axis legs, have their own motor controller, as you can see here, right? So we've got basically like this pitch and then yaw is how it's structured now. There's a lot of different ways we could wire this up, right? All these different pre-motor modules, though, do the babbling, right? So they'll have these like random things, and it is doing a kind of reinforcement learning. But the signal that it's learning from is the most important part, right? That is the output of the EPMs that are being driven by the inputs from the body, right? So we have the joints. Basically, the position of every single joint goes to a joint EPM, and the IMU, right? Which is sort of like our proprioception there, right? Sine, cosine, yaw, forward speed, and angular momentum, angular speed, right? So that's our IMU. There's an IMU EPM, and there's a joints EPM. So really the only thing this guy is aware of is its body relative to space, how fast it's moving forward and backwards, and what are the position of its joints, right? So we still have our neurochemical pathways wired up from beginning to end, and our descending predictor. So this is a complete active inference loop. We've got our homeostatic drive. Those are wired into the pre-motor controller. So all of these things are connected the same way we've been doing it. It's just now in this kind of quadruped context, which has a lot more degrees of freedom, and it's a lot easier than it was with Cell and with playing Pong and all those things. It's actually easier for it to learn these dynamics, I think, because it actually has a nice topology to actually work from. So let me bring up the inspector. I should be able to do that here. We can take a look at what the EPMs are up to. So let's look at the joints EPM. So, the neural graph is nothing crazy, but I really like watching the PCA scatter plot. I think this is actually a really interesting way of seeing. So this is basically plotting all of the embeddings that are happening continuously, right? This kind of is a way to explore the space of the embeddings that are coming out of this, the joints, the joints EPM, right? So the encoder, we have our standard geometric encoder, which is generic. It just has all the joints coming in, and you can see them, coming out over the actual stream of embeddings here. But what we can see is that there's a new node that was created. So it's kind of creating this kind of boring looking graph, but really, we're having nodes that are baking, right? Like it is doing the real EPM situation where this is our JEPA, right? We've got our TLE that's saying what nodes are interesting and what areas are interesting and what aren't. The nodes are getting baked here, and that's what's firing out of the reality tokens, right? So this is a real EPM doing real work on the joints. Let's take a look at the IMU. That's a little bit more interesting, a little bit more two-dimensional. So let's look at the PCA scatter here. It looks different, right? These are two totally separate sensor modalities. The EPMs don't care what kind of sensor modality it actually is. It's actually, creating nodes. And, nodes are getting baked. Nodes are being created on the fly constantly. I think we finally have the dynamics dialed in, where these EPMs are functioning very well on their own, right? So look at this thing. It's I don't know what the body's doing right now, but it had that very interesting structure. It was going over and over again in that one area, right? But already, nodes are being created, they're baking, but they also die. So there's actually, inside of our growing neural gas, there's a life cycle that these nodes perform in, right? So if they're not baked, and they're growing, they will die off, right? So technically, this thing is adapting to its environment. There's plenty of dynamic ways of making these knowledge graphs stay more bake for longer so we don't forget things. Very, very easy to control, very discoverable when it comes to what's actually happening inside this thing. You can track the input to the output and back again very, very easily. This is not a black box, right? When you're working inside of a system like this, everything is linear, right? Let's see what we've got here. This is like basically the a Hebbian graph for the premotor controller here. You can see the spikes firing. We've got these policy output modulators. Interesting. It's working. I just rarely look at this display. I designed it, and now I'm like, well, look at it. It's got a lot of pretty shapes. Either way, it doesn't really matter. Not until we actually have problems do I go back in here, and we may have even changed the underlying structure so that this is maybe not as relevant. I'm not really sure. Doesn't really matter. The actual spiking aspect here is working properly. We do see the latents changing, and those are feeding back into the descending predictor, right? Homeostatic drive, we get to see the just these two graphs here, urgency and alive. I don't think, haven't wired anything up for this yet. We just get to look at the JSON. This is the lateral voter. Wow, look at this. The associations are actually turned off. We don't even have the Hebbian matrix wire turned on. It's just not necessary yet. So at this stage, though, this is where I'm going to be testing a couple different, now that we have curriculums wired up, we can do a additive test, right? So we'll add one feature. Maybe we'll just turn on the Hebbian association matrix for the lateral voter, right? See if that changes anything. See if it moves anything off of the baseline that we have right now. The joint, I don't think we need to change the EPMs. These things are pretty well baked. The neurochemical state is just fun to watch, as things happen. Actually, let me flip back over so we can watch our little guy maneuver himself around. Where are we right now? We're in the, okay. So he needs to rack up 5 minutes worth of standing stable before he can move on to the walking stage. So he's in the stage now where he's flipping over, right? So however long this video's been. So he spent 3 minutes being wobbly. And as soon as he crossed over into being able to stand for 1 minute, we kind of get into this phase here where he will, the height, remember the height of the chassis above the ground is the reward mechanism, right? Is being fed back into the system here. So it's choosing places inside, it's choosing consensus tokens that represent higher, right? That's what it's reinforcement learning off of. But it makes total sense that it's pushing himself higher and higher, even though he's being penalized for going above 0.85. The cool thing about homeokinetic learning from the Playful Machines paper is that it's going to try to push the boundaries as much as possible. So there's only a small signal of it like tapping the upper boundary right now, and it hasn't quite learned how to get past that. So it's going to go through this phase where it flips over a bunch. Totally fine, right? It needs to do that. It needs to find the edge and then figure out how to kind of pull itself back from that. And what I've seen, it takes about 20 minutes of wall time for it to get to the point where it can stay standing for longer than 5 minutes, right? Totally works. Now, and after that, we're going to get to some kind of walking. As you can see, it's stumbling around now, just trying to stand. You know, what I might do is actually have it try to stay within a certain XY, like stay within the circle here during this standing stable phase, maybe penalize it a little bit if it goes too far away, to really get it so it can stay in one spot. That's a useful skill. We don't want this thing walking all over the place. But one thing that does happen if you just let this thing go over time is that it does find a equilibrium where it's not walking around as much. You start to see his little footprints here stay more or less in the same spot. But until it can stand for longer than 5 minutes, it's going to sort of like stumble around like a drunk spider. And look at this. This kind of this is a pattern where it'll balance on one red leg and one yellow leg, and then the two green and the blue legs are its little balancing arms. Absolutely fascinating. Why? I have no idea, right? This is fully symmetrical, but doesn't necessarily matter. You know, like when to, you know, like we have random. There's enough random stuff in here with this particular seed. I think I'm using seed 44. Everything is completely deterministic. So if I rerun this test in seed 44, all the random number generators are going to receive that same seed, and I can repeat every single experiment exactly the same way. But this is really encouraging. You know, we've got our reinforcement learning component, which is our premotor controller, but it is being fed by real information that is not deterministic, or that is not directly from the world. You know, these EPMs are sitting in the middle. We could wire this up to cameras or anything that we want, but right now, you know, what we learned was that the joints in the IMU were the thing that made it the most stable for standing up. So we want to add components very carefully. We want to look at this wiring very carefully. We don't want to change too many variables too soon, even though it's super fun to experiment. We're just going to do one step at a time. But I would say this is a massive step in the right direction, that we've actually got a complete active inference loop happening, and our guy is learning. And it gets better over time. The longer this thing stumbles and falls, the more it actually learns. It doesn't get stuck. That's a huge deal. What we're going to learn next is, see, this is another thing that'll start to happen. This yellow and red, like the red leg getting stuck underneath because it does help get the chassis higher, is a pattern that I've seen before in this seed. And it'll get past that. Right? The fact that it gets past it, we've got nodes that are being created and destroyed inside of the EPMs. All that kind of stuff is fully dynamic, but it works. Crazy. So I'll check back in again when, if we get this thing actually walking around in some kind of coherent way that's not quite so drunk. Say hi. Love it.